My name is Ivan Lassa. I'm a senior consultant with GPI. With me today is Paul Vinnick. He is Director of Coatings and Cathodic Protection for GPI. And the intent today is to talk a little bit about cathodic protection of reinforced concrete, share with you different materials, different methods of applications, as well as systems, and how each of these systems can actually be a useful tool to prevent corrosion on particular bridge components. The way we're planning to do this, we're going to start with a little presentation to explain what cathodic protection is, share what the materials that we use when we apply cathodic protection for bridge applications. And then, of course, we're going to be open to questions. We have an entire hour to share with you guys and try to bring light to some of those of you that are not all that familiar with what cathodic protection is and how you can use it on bridges. And we do have a little some hands-on experiment here that we can to demonstrate the cathodic protection concept. And at that time we can all move over here and we can take some potential measurements and so forth, so you will understand a little bit better how is that cathodic protection can control corrosion on your structures. But without any more delays, let's go ahead and let Paul take over, and he's going to start with the presentation. And we probably both participate on the presentation, but it's he's going to take the lead, and we will proceed as we finish. Thank you. Paul?
Thank you, Ivan. Ivan has been my mentor in the field of corrosion. He and I have worked together a long time. Combined experience in bridge preservation, I guess, a little over 50 years. Indeed. So we're hoping to bring some good things to this morning, and with that, I'm going to get started. The first thing I want to point out is there seems to be some myth out there that cathodic protection can cause corrosion, and there are a lot of non-truths. But anyway, this is NCHRP Synthesis 398, and it very plainly states that in the conclusion, agencies that have successfully implemented cathodic protection technology have experienced a reduction in the frequency and cost of bridge maintenance and an increase in the service life of their bridge structures. Now, there's also some FHWA publications out there, same thing, but that's a pretty conclusive conclusion to me, and wanted to share it, kind of dispel some of those myths. Durable bridges, can they be done? Well, this is the Progreso Pier. It's located in the Yucatan in Mexico. It was built in 1941. That's the top picture here. It was built using stainless steel reinforcement. In 1969, they built another pier, and here it is today. So it's 81 years old. Well, that was in 2017. We can fast forward the math. What's that make it? 86 years old. In 2017, I looked up the maintenance costs. They booked $7,000 maintenance costs in 2017. It's a 6.5 kilometer structure and jets out into the Gulf of Mexico 4 miles in a very southern latitude. Those are excellent results. So how do we eliminate corrosion of concrete bridges? Well, in pre-construction, we can do it with design. We can use alternative reinforcements, non-corrosive materials, etc. Once design's done and we're done with construction, the only tool left is really cathodic protection. Once the chlorides are in your concrete, cathodic protection is your best tool. So how does cathodic protection work? Well, it's just like the anode on a boat motor. It provides a current to the steel. So the anode is a higher energy metal. And that's why the current flow from the higher energy metal to the lower energy steel. And that's in essence the circuit. Current flows from the anode into the steel through the electrolyte, and the current flow is back out. And so that's our whole circuit. Part of the circuit is through the electrolyte, part of the circuit is a metallic link between the two metals. We won't get too deep into the principles of cathodic protection today, but I wanted to at least give you the basics and the overview. We're going to try to focus more on materials and demonstrations. But if you have any questions, just stop me and we'll try to get a good answer. Impressed current, the same identical principle as galvanic, except instead of utilizing the anode itself to provide the power for the protective system, we're now going to use a DC power supply. Plugged in, we'll get AC power, we'll rectify it to DC, and we'll use that to energize our circuit. So how are we, in words, how does this work? What's the cathodic protection mechanism? Well, current polarizes the steel to the extent that all anodic sites become cathodic. That's language right out of the AMP references and standards. And essentially, if you don't have any anodes, corrosion occurs at the anode, right? If you don't have any anodes, you don't have any corrosion. That's basically it. Polarization current is supplied by a piece of metal, zinc or magnesium, usually. And those are higher energy metals, higher potential energy, so they pass their energy to the lower energy steel. Otherwise, we use the DC power source like we just said. And both of these systems donate electrons to the metal. So what is polarization? I want to give a very kind of basic illustration. You turn on a fluorescent light, right? When you turn it off, does it go off immediately? There's always like a half a second or a second that it's still on after you hit the switch. Well, the gases in that fluorescent tube are still polarized, and you're still seeing the light. Now that energy dissipates a lot quicker than the energy we're talking about with a concrete bridge, but it is still, I think, illustrative of the whole principle of polarization. It's just whatever we're polarizing is holding on to that energy for some amount of time, and that's polarization. So why is CP better than traditional repairs? Well, chloride compromised concrete must be removed. If you're spalling and having issues, you're already in trouble. So normally the rule of thumb is about 1.2 pounds per cubic yard of chlorides. That can change with your mix design, your alloys, things like that, but it's still a pretty good rule of thumb. If you test your concrete and you have higher than 1.2 pounds per cubic yard, you're past what we call the initiation phase, and corrosion will begin. Incipient corrosion, also pretty commonly called halo effect, is what's depicted in these pictures. On the left, you can see a concrete repair, and you can see the spalling extending vertically up beyond the repair. On the right, you can see what looks like at least 1, 2, 3 repairs. You've got the green, the yellow, and it looks like black. And the owner here is chasing it. They do the first repair. The corrosion begins in the second area right adjacent to the first repair. They come back and they fix that. Well, now we've got corrosion occurring in the next section just adjacent to it again. And we see this all the time in bridge decks, all the time in substructure. And the reason is this concrete up here is still all chlorinated and still very electronegative. Down here, we've just put in brand new concrete that has no chlorides. That sets up our corrosion cell. We've got a high energy area and a low energy area. So unless you isolate the bar and do some things to prevent that, you're just going to chase your tail. Where can CP be used? Well, cathodic protection systems are available really for all reinforced concrete components on a bridge. If you've got a reinforced concrete component, CP is a candidate. That includes bridge decks, caps, beams, piles, etc. ICCP, impressed current, utilizes a noble metal anode, typically titanium, and an electrical power source to control corrosion. Now, why titanium? They say it's dimensionally stable. You know, when anodes corrode, they lose their base metal. So you're losing zinc, as that zinc protects your steel. It's going out into the electrolyte. With titanium, you do not lose any of your volume of your anode. And so it's a long-term type of anode. And that's why they use titanium, and you'll hear, well, let's just move on. The sacrificial CP uses zinc, aluminum, or magnesium anodes, and these anodes, they lose volume as they sacrifice to protect the steel. So in practice, each structure has to be evaluated, and you have to do a corrosion assessment for that specific structure. Can't emphasize that enough. That's the only way to determine the best system and the best materials, period. So just to demonstrate the type of decision process, do we want to use impressed current or galvanic? Well, are we going to do 6 random piles, or are we going to do 8 pile bends? Do we want the system to last 5 years or 50? Those are the kind of questions and things that have to be answered to design the best system for that structure. As far as maintenance, galvanic systems, rule of thumb, this is from our days at FDOT, galvanic systems are inspected every 2 years. Impressed current systems, on-site inspection every 6 months. Either of these systems, but normally only ICCP systems are on telemetry, and they can be monitored 24/7. This is another one of the things that kind of my pet peeve is, people say, well, CP systems are expensive to maintain. How do we maintain them? We don't have staff to maintain them. And my comeback is, well, what transportation infrastructure can we put out there that doesn't need to be maintained? So they have to be maintained, and these are kind of the inspection frequencies. We really need trained individuals out there. CP is a very specific niche, and having trained individuals do these inspections is also imperative. So unlike other transportation investments, though, except toll plazas, CP extends service life, and that returns money back to your budget. So the CP selection process, how many additional years of service are we expecting? We mentioned that earlier. Will monitoring and maintenance service for CP be available? Do you have the staff? Do you have the consultants? Do you have the budget? What type of components to be protected? Are we going to do a pile? Are we going to do a pile cap? Are we going to do a bridge deck? What type of reinforcement is in the component? Is it epoxy covered rebar? Or is it just plain steel? How many components on the structure? Is electric available? Or do we have to rely on site electric generation, whether that be solar or some other? And how big is the bridge? So, of course, money comes into all projects. So CP materials. First of all anodes need to be specifically manufactured for cathodic protection. Hopefully that's pretty straightforward. The properties of the anodes are, for the most part, very similar. You know, they're titanium, they're zinc, and they have to meet ASTM or NACE. It used to be NACE, now we're AMP, but meet the standards that are provided by these organizations. The grouts and concretes used to distribute the current. We talked about that circuit. The concrete's part of that circuit. And we have to use cementitious materials that are approved by the anode manufacturer, and these are generally lower resistance concretes. We want the current to pass through them. We don't want a high resistance in that concrete. Power supplies and remote monitoring equipment also need to be fabricated for cathodic protection. We need to be able to interrupt the circuit to get our off potentials, and we'll talk about that in a second. The wiring must be 10 and marine grade, you know, the stuff that's used on boats and in marine industry. All the hardware has to be 316 stainless. Here's some pictures of some of the titanium mesh anodes for ICCP. These are not used for galvanic CP, just ICCP. They're dimensionally stable, again. They're tested to NACE test method 0294 or ISO. I'm not as familiar with the ISO numbers. There's 3 manufacturers in the market and only minor differences in their products. These easily conform to the structure of to the geometry of your structure, and they're available in 3 output capacities: 20 milliamps, 30 milliamps, and 40 milliamps per meter squared. Here's a picture of an installed titanium mesh. We've got plastic pins holding the mesh down and a distribution bar. The anode mesh is composed of metal oxide catalyst centered to an expanded titanium mesh substrate. And I'm not an expert in the manufacture of these anode meshes, but my understanding centered is, they take a metal oxide, so that's a metal that's been combusted essentially and turned into an oxide, and center that onto the mesh as probably a gas. The anode's secured typically with just plastic fasteners, and that keeps it straight and no buckling and things like that. Some more pictures of titanium mesh anodes being installed. Here's one that's already installed. We've got the reinforcement over it. Here's one that's being encapsulated with shotcrete. So we have to encapsulate these with either shotcrete or concrete, formed or sprayed on. Current flows through the encapsulation, through our cementitious material, and the old concrete to the reinforcing steel. So this has decades of proven performance. The ICCP systems maintained really have an indefinite service life. That titanium anode will last longer than we will. So, but there's only 3 manufacturers and several distributors. Here's a picture of a ICCP pile jacket. So we've got the encapsulation of the titanium mesh anode. That's inside the jacket. We just saw a picture of that titanium mesh. Well, that mesh has been placed inside this jacket around the existing pile. It's a stay-in-place form. It's placed around the pile. There's an annular space between the mesh and the existing concrete. And so you can see where it's been filled here at the top. Additional reinforcement can be added if you need to get back to your original structural capacity, or you want to increase structural capacity. And we can combine several piles into just one CP circuit. CP in concrete doesn't require anywhere near the amount of energy that CP in the oil and gas industry. So with one rectifier, we can power several circuits. The wires are routed in conduit, and you can see it in the picture here, where the wires are coming in and out, to get to our monitoring stations and things like that, and to our rectifiers. Uses standard titanium mesh, and again, years of performance with adequate power supply maintenance. Some more on the ICCP anodes. Here's a titanium ribbon anode, where we cut a groove. We place the anode in the groove, and then place the cementitious material over the anodes. Multiple manufacturers and suppliers, and has multiple uses. It's available in various dimensions and openings and geometries. Different mixed metal oxide coatings are available that can change the maximum output. So, how much energy can we send to that anode is dependent somewhat on the manufacturer and which metal oxide was used. Let's see if I covered all of these. We've got the groove cut. The grooves are filled with water. The ribbons are connected to form one circuit in the component. And the spacing of the ribbons are pre-engineered based on the cover and electrical resistivity of the concrete. And that makes perfect sense, right? Because we're pushing current through the concrete. So if the resistivity of the concrete changes, we got to kind of engineer our system to take account for that. That's all that's saying. Some more on the titanium ribbon anodes. Here's a picture of one in place. Notice the plastic wire ties. The titanium substrate of these anodes conforms to ASTM B265 grade 1. And this is just one of the manufacturers, an excerpt from their product data sheet. It's 10 millimeters wide. I don't know if you can read this back there. It's a little small. 2.8 milliamps per meter squared. I believe that's per meter squared. And then also the anode surface area is given as well. Let's move to discrete tubular anodes. These are also for ICCP. These are not all that frequently used. They're cylindrical, made of titanium and ceramic composites. They're embedded in holes, cored into the concrete, and sealed with a conductive grout. Same thing again, we need a conductive grout to get our current out and back to our steel. All the wires within one cathodic protection zone are spliced together and routed into cut grooves and then into conduit to the rectifier. We need extreme caution. You don't want your anode contacting the reinforcement. That's a no-no. And you can see in the installation here the little straw coming up out of here, and you can see it here. With ICCP, your anodes can produce gases, so we don't want those gases being trapped in the concrete, and that's all that straw does, is it gives a little bit of a vent and allows those gases to be released out to the environment. And you'll see this also on oil and gas pipelines. If you see a oil and gas pipeline underground, you'll have a U-tube. You'll see it coming out in a vent to vent the gases from the same phenomenon. So here's a graph that's kind of depicting the anode service life at different current outputs. And the real gist of this is the more juice you put to that anode, the lower your service life is going to be. That's what we're trying to convey here. So current and service life. Let's move now to impressed current cathodic protection anodes. Arc sprayed anodes can also be used in galvanic CP, but
not only for ICCP.
Yeah. In addition to zinc, other metals can be used when in ICCP mode. Requires a complex surface preparation to ensure the proper bond with our concrete, and the chemical composition of zinc wire shall contain 99.5% zinc as a minimum. So it just flame spraying zinc onto concrete, essentially, and then connecting that flame spray either to an ICCP system or to a galvanic system. Some of the equipment involved and the technology, here's a guy actually doing it. We've got the 99.5% zinc. It's got to be directly connected to the rebar, and we've got AWS C220 provides the specifications for application. And here's kind of a summary. We've got the wire coming in, we've got a shroud, contact tubes, an air cap, and then we've got an arc zone right here that's vaporizing the zinc and propelling it out to the concrete. Just one more picture of a guy applying the arc spray. So let's get a little deeper into the jackets, the pile jackets. Those are the really, at least from my experience, the workhorse of CP. In what we've got is a fiberglass or polymer jacket. We've got either a zinc or titanium, depending on whether it's galvanic or ICCP, mesh that's installed inside the jacket. We've got spacers that maintain our annular space, and this is placed around the jacket. We've got our monitoring box, and it's pumped full of the grout. Here's more of a design drawing type sketch of it. The pile jacket provides the protection in the splash zone and above. So our water line would be somewhere around here. We have a 50-pound bulk anode that protects the pile below the water line. So we have two different electrolytes here. Up here, we've got concrete. The anode is directly in the concrete, and it's concrete to steel, right? That's our circuit. Down here, we've got water, and we have concrete, and then the steel. This is only recommended for application in contact with seawater. There are two manufacturers of the product with a minor difference in chemical composition. The anode mesh Yeah, we're talking strictly, I'm kind of mixing up zinc and titanium. This slide is supposed to be specific to just galvanic. So when it comes down here, and it's the bulk anode is standard whole zinc anode conforming to B418. That's the zinc for the galvanic zinc mesh used for galvanic cathodic protection. A minimum thickness of 1/4 inch is recommended for the FRP form corners. So more galvanic pile jackets and bulk anodes. They're activated zinc anode jacket. The anodes are placed externally to the structure. In this instance, you can see them here. The anodes are then encapsulated in the concrete using stay-in-place forms or removable forms. Very good performance on dry concretes, and unfortunately it's only single source availability. Some more pile jackets and bulk anode information. The anodes can also be, the bulk anodes can be installed in the jackets just the same as the zinc mesh. Anode bars are covered with an alkali that's activated grout to keep the anode active. This chart is showing the stability of zinc. So you can see the curve here. What we're trying to convey is that above pHs of 12, zinc becomes very active and corrodes. Up below pHs of about 6, it also becomes active and corrodes. So in this area, we're pretty good, and no corrosion takes place. But in these areas, that's where our zinc becomes active. So activating to a pH of about 14 increases the zinc activity, and they utilize encapsulation materials around the anodes to keep the zincs active. And they can create their own corrosion products and deactivate themselves. These encapsulation products help keep that from happening. Here's a picture on the right of some submerged bulk anodes hanging on, I can't tell, it looks like channel.
Yeah.
These anodes are mostly used to provide cathodic protection structures with underwater corrosion. Magnesium is more for fresh water, and zinc mostly utilized in salt water. Similar zinc anodes are used to complement galvanic pile jackets. Again, we use the pile jacket in the splash zone. We use the bulk anode below the waterline. Here's a couple pictures of some finished installations. On the left, you can see these are solar powered ICCP. You've got your junction boxes where the conduits are coming up. We're joining wires, connecting circuits together. We've also got our monitoring box where we can come in and check the effectiveness of the system. The same on the right. You've got your conduits coming up, joining wires. We've got monitoring stations. Ivan, what's that one?
That is a monitoring port, such that we can externally place a reference electrode initially and in the future, so we can actually accurate for the service life, for the service time of the system. We can monitor at the same location.
Some more finished installations. On the left, we have galvanic arc sprayed zinc. On the right, we've got pile jackets, galvanic pile jackets on the two outer piles. We've got a standard conventional pile jacket in the middle, and as you can see, the spalling protruding through the bottom of that jacket, it's not. And it's actually deleterious because we can't see how bad the corrosion is behind that jacket. And so what we got here, we've got the same jacket. This is galvanic, so we've got a zinc mesh anode inside that jacket, and we've got a 50-pound zinc bulk anode somewhere down here below the waterline. Continuity. We always hear about continuity with CP. Well, thankfully, NACE has a SP308, and that tells us how we can go out and test whether our steel is continuous or not. And what it tells us is it's got to be 1 millivolt or 1 ohm. And all steel that's to be cathodically protected must be electrically continuous. Verifying continuity should be part of any CP system project. And that's why I mentioned the epoxy-coated bar earlier. Epoxy-coated bar, it can be made continuous, but what a nightmare. Electrical continuity can be constructed into new structures for future cathodic protection installations. Yeah, essentially, it's a lot easier to make your rebar electrically continuous before you pour your concrete. Typically, new specifications indirectly provide for continuity, so it's not even all that much of an add. You know, we're using steel wire ties anyway. It's just a matter of making sure everything's continuous rather than just throwing it together without any oversight. This is a picture of the Howard Franklin Bridge. This is a large bridge. It's Interstate 275 across Tampa Bay. I can't remember. I think it's 120,000 DT. And most of those people are on there right now. Still. I've traveled that bridge many times and it is a headache and a nightmare. But the real gist of this is there are 92 channels on this structure. This structure's been cathodically protected since the late 80s. And this is some of the telemetry that comes in. I mentioned 24/7 earlier. Well, this was monitored at the State Materials Office in Gainesville, 140 miles away. And what have we got here? We've got our off potentials and our on potentials. So let's see if I can read through. This would be footer north side on potential, footer north side off potential. So NACE tells us that if we can polarize a structure by 100 millivolts, that it is cathodically protected. And that is a rule that has been proven over time. It's utilized in the gas industry and oil industry where big, huge explosions take place if you have corrosion. So it's trusted is what I'm trying to emphasize. And that's what this telemetry is giving us the ability to compare our structure to the criteria. Focal points for cathodic protection or inspection. Things like wiring, spacing, conductivity, and grouting. Ivan was just telling me about a project, I guess, that the bulk anodes were installed and never wired in. You know, we're paying for them to be wired in, but if you don't have inspection and qualified inspection, you may not ever know. You may come back 30 years later and wonder why your bridge is falling apart. Galvanic CP is simple. I want to emphasize that very much. You know, it's so simple, we've got it in this pail right here. We're going to show you in a few minutes. It does have a shorter service life than ICCP, but it's much simpler. So pros and cons. And you always want to use materials and practices that are designed for CP. You know, utilize materials that are made for this purpose. ICCP requires conduit and wiring and power supplies and electrical work. I'll break right there and just say, you know, that is CP. CP is electrical circuits and chemistry. We talk about an electrolyte. There are reactions going on in that electrolyte. Those are the two facets of cathodic protection. And so here, you know, we're talking about the wiring and the power supply and the electrical work. ICCP requires frequent monitoring. FDOT is every 6 months, and maintenance over its service life. Being able to monitor these systems remotely is strongly recommended. Electrical systems like this, at least in Florida, where we get a lot of lightning strikes, that's one good reason that you want to be able to monitor them 24/7 and know when your system goes down. Monitor and maintenance staff require basic CP training. You know, we don't need designers to go out and do the inspections and measure our potentials, but we need staff that understands what they're doing and the importance of doing it right. You know, bad data is useless. There is a course. Ivan and I worked hard to get this course brought to the United States. It was originally developed through the Australasian Corrosion Association, and NACE brought it to the United States. It's called the Cathodic Protection of Concrete Structures and Buildings. It goes through how the components in a concrete mix design affect durability. It goes through realkalization. It goes through CP methods. It goes through alternative reinforcements. My personal opinion is it's a very good class. I encourage anybody that's going to practice in the corrosion of concrete and cathodic protection and wants to get more knowledge in this area to take this class. It is specific to concrete structures and buildings. And that ends this portion of our presentation. So I don't know, I guess maybe I'm a little ahead of time. I usually do go pretty quick. Any questions on the oral presentation?
With Florida, I'm sure other states, but I can only speak to Florida, of course, our older structures are, they had a less durable concrete, often a lower strength concrete. We're now working with denser concretes, higher strengths. We're adding admixtures and stuff, but still looking at it solely from a rehabilitation. We talked about the testing the existing concrete so as to determine its conductivity. We've got to flow from the anode through our new route of concrete into the existing. How does that older concrete compare versus newer concrete? Which one is more conductive?
The old.
The old.
It's full of ions. It's full of chloride ions.
Okay.
And the have a greater porosity also. So that old concrete is saturated with water as well as with chlorides. Chlorides are negatively charged, so they are making the concrete more conductive. So it is good. It is a good corrosion engineering practice to go ahead and measure the conductivity of the concrete, because there is instrumentation and there are tests that tells you how to measure the conductivity of the concrete. But as a rule of thumb, if you have high chloride, that concrete is very conductive, and that's why you have corrosion there.
For the telemetry, what kind of hardware and software requirements? Is it pretty simple, straightforward system that you need for it?
Well, yes, I believe so. There are off-the-shelf PLCs and things that can be used for that purpose. You know, you've got to have them in enclosures that are rated for that type of environment, and you want robust. I say PLCs, and this is a little bit different because FDOT's used PCs for a while, but the PLCs that I've been exposed to and used are built for the chemistry, for the chemical process industry, and they're very robust and made for harsh environments. And so any computer can be linked to the instrumentation that's needed to do CP. It's getting that equipment into the environment and protecting it from our harsh saltwater environments in our bridges. So, but if you've got any experience with instrumentation and bringing in voltages to a I/O board and then into a PC, it really isn't all that complicated. The portions that I'm going to let Ivan speak to are the phone system, the satellite phones and transporting the data.
However, need to make sure that, and we added, it was part of one of our slides, it has to be certain components that are specific for cathodic protection. For example, you cannot just measure the voltage. You should be able to remotely interrupt your circuit. The reason for that is because this is for cathodic protection. We're trying to ensure that true cathodic protection is being provided. So if we go to the criteria says that the instant off, that is a terminology that says that what it means is that you are applying power, and when you immediately you interrupt your circuit that cut the power off, you measure the potential of the steel, and that instant potential there is what tells you the polarization, and is what is going to tell you if you are providing sufficient cathodic protection. So it has to have certain components. Another one is that it has to have some kind of a voltmeter that measures small amount of current, because in most of these impressed current cathodic protection systems for reinforced concrete, for bridges, we talk about a very small amount of currents. So those currents, they're going to be ranging in the from 30 milliamps to perhaps 200 milliamps. And some of the instrumentation out there is for regular household. They will only measure 120 amps, for example. So those little components, they have to be part of your telemetry system. The other thing is, how are you going to get that all that information to your office. Normally, the most common is using cellular telephones. Because a cellular hotspot or cellular modem, nowadays there is cellular signal everywhere, and you can just dial that number and connect to your unit. Now, having said that, it has the pros and cons. It's indeed is probably the most common and routine thing to do. On the other hand, you're bound to whatever the cellular companies want to do. If they want to go from LT1 to LT5 and then you have to be changing your modem, because then they upgrade the technology every 5-6 years, and now your modem does not match it. So that's the only thing. Well, you have satellite communications also. You can link it. If it is a short trip that you have some telephone line nearby, you can put on your DSL and send it over to the office. Any other questions or discussions or opinions?
I'm going to ask a quick question, and this is really kind of very specific, and I'll ask it to the whole crowd. There's other corrosion people in here. On your TSAs, right? When your thermal spray anodes, particularly on girders, pre-stressed girders, we're providing CP systems on there. We have some systems or some requirements on the TSAs in North Carolina particularly, and I think it's probably more for high-rise structures where you're not as close to the water and you're not as maybe it's drier, what I'm trying to get to. And so we have the makeup of the TSA is zinc, aluminum, and indium, right? Mm-hmm. So the indium helps to engage the system.
Yes. And
so we'll have the specifications might say, 0.2% indium or whatever that percentage is. The question is are those percentages exact requirements, or are they like minimums? And
no.
So if somebody submits and say, if we say, and I'm just throwing out wild numbers because I don't know it that well. If our spec says 0.2% indium and they submit us something and it says 2% indium, does that matter?
Well, actually, all depends.
Okay.
It might matter.
Okay.
But just to be honest with you, normally with these alloys, what that the chemical composition just is going to govern the output, how much current they can put out. So a variation on the chemical composition can decrease or can increase the output. Normally, it doesn't make a difference on that. Because like I said before, the currents that we're talking about here, they are so small that if you have a little variation, it really, regarding the Cathodic protection part of it, really might not make a difference. However, since we're on the topic, we need to also comment on the fact that those chemical compositions will also affect the rate of self-consumption of the animal. So depending on where you are, that might be very significant. And in Florida, we use 8515 for metallizing, which is 85% zinc, 15% aluminum to make it active. The humidity in Florida is so high that the 8515, it is true that it has a higher output, it sends more current, but it self-consumes so fast. We saw instances that it self-depleted within 6 months. So we decided not to use that one and stick with the zinc on 99% zinc rather than the 8515. On other places, more drier places, the 8515 is the way to go. because it keeps it more active. So the chemical composition, it makes a difference. But when we talk about from 0.0% to 0.02, that might not be a big issue really.
And kind of, I look at that principle with the same as like the higher stainlesses. And I can't remember, but is it austenitic? But one of them is the amount of molybdenum in it. And if the impurities in there are affecting the corrosion and the patina that's formed. And it's the same in the anodes. These little nuances in the chemistries will affect the oxidation products and affect the anode overall in that manner.
And there are little tricks of the trade, like we were showing over there, that on the pipe jackets, there are going to be, it is good to request increased thickness on the corners. Reason for that, because some of the pipe jackets that we were showing, they are in the water, and there is a lot of water, marine growth that starts getting inside the jacket and start pushing the jacket out. And most of the time it breaks in the corners, so let's reinforce the corners. Little things like that are the things that you need to be looking at. For the most part, there are manufacturers that they do have already integrated systems that you can specify. But then in your special requirement, you need to have somebody on your side that is familiar with the technology and tell you what to add to the spec and things like that. Basically, we were talking about cathodic protection and the concept, and Paul was showing how the current flows from the anode to the rebar. The rebar is the cathode. As it was presented on one of the presentations yesterday, I think it was Natalia, showed a corrosion cell which requires to have a cathode, an anode, an electronic pad, and an electrolyte. Okay, so cathodic protection is basically the same thing. The only difference is that the anode, now we are establishing the anode on a different location outside the concrete. So basically with this exercise here, what we have is a demonstration of that, and also we talk about potentials. What is the potential? Potential is the energy that the rebar has. So that's what we want to change. We need to be able to control that, and we use that in cathodic protection via controlling the current part of the chemical, of the corrosion cell.
So, showed the circuit for galvanic CP in the previous presentation. We built that circuit right here in the pail. And that's very simple. I mean, we can build it right here in the tabletop, and we've got it demonstrated. So right now, you can see we're at 167 millivolts, minus 167. That's what we would call our native state. I don't know, have transportation lollipop. Everybody familiar with these? These are, it's just a piece of rebar in a what is it, 5,500 PSI concrete. Standard DOT stuff. And in fact, this came from the State Materials Office at FDOT. And so, native state, this is just the lollipop. The zinc is not in the electrolyte. We've got our electrolyte here. We've got a reference electrode, copper sulfate, reference electrode. And so our circuit is from the rebar through the concrete back to the reference electrode over to our voltmeter, and then back from the voltmeter to the rebar. That's our circuit. It's the same circuit we showed in the slide earlier. And our native potential, 167.6.
Yeah, that is the energy that is by nature stored in the rebar. You know, when they fabricate, when we make the rebars and when they fabricate any metal, you know, they use a lot of heat to mold it and get it. So all that energy is built into the rebar itself, and it shows itself in a matter of in an electricity form, a voltage form.
We're just measuring it.
And we just, with a reference electrode, we can measure the voltage potential of different metals. Basically, if you remember a little bit of chemistry, we have the electromotive force, less, right? And it shows you the value, the energy of different metals. So in this particular case, in the particular case that we have in here, we have the steel, the rebar. We know what the potential is because we can measure that. And then we can introduce the external anode, right? And if you monitor the potential there, 167.
I got it.
When we introduce the anode on it,
That's a block of zinc.
this is a block. This is zinc at this time. We're going to put it on within the electrolyte. Oh, you computer. What happened?
Timing is everything.
Okay. So when we have the zinc anode and we introduce it within the electrolyte, that means that the seawater are on the pile. I'm not looking at it, just look at the meter what it's saying.
Minus 0.413 volts. So 413 millivolts.
So it was a dramatic change on that. Okay, so now we are applying cathodic protection. Okay, so we want to verify if how much cathodic protection we're going to be providing. According to the standard, like Paul mentioned before, we need to polarize a minimum of 100 millivolts. So what I will do is I will pull out my anode to actually interrupt the circuit. What I was telling all the RMs, you need to interrupt the circuit, and that potential should immediately change. So the instant, the first reading that we can get in there is going to be what is called the instant off. Okay? There you go.
Minus 618. So 618 millivolts.
So it polarized from 400 millivolts.
Yes.
So in that amount of time. Now it's going to keep going down. Eventually, it will go back down to 160 or something like that. You know,
Back to native.
back to native. But because we only showed a little bit of cathodic protection now, on more mature systems, you know, that we have had the system, the pile or the component on the cathodic protection for 3 or 4 years. When we interrupt the circuit, it's going to start going back to the anode, to the native potential, to the original potential, but it might take months on that. And all that means is that on some of these systems, even if there is something goes bad with the particular system, it's not going to start corroding right away. You know, it's still going to be functional. There is going to still be some residual protection there, and like I said, I live with the galvanic system. That was what Paul was referring when he said that he prefers galvanic system because they are very simple. There are other circumstances in which you cannot use galvanic system. You have to go in press current. But with impressed current systems, remember then that all the current that is applied to the rebar is provided by a external power supply, a rectifier or a solar panel, and things like that. And those are also very susceptible to power surges, lightning on the bridge, and all that. So that's what we recommend if you have an impressed current cathodic protection system, to have a telemetry system, so you know that a telemetry system attached to it, so you can monitor from the office at least once a week. Look at your data and say, oh, it's still working, no big deal. Because then if you only visit the system once a year, and there is a lightning that occurs right after you leave, then it's going to be a year before somebody discovers that has not been working. So So that's the reason why we said telemetry is very strongly recommended for ICCP systems.
I have a quick question.
Sure.
The monitoring and telemetry, who at FDOT does that?
Pardon?
Who's generally the one monitoring the telemetry system?
Well, initially, the materials office.
Okay.
Materials office has a corrosion lab that is set up to monitor this system and to provide maintenance. If something goes wrong, they just send, they have staff that they can dispatch right away. But now they have been, like most of the DOTs, there have been some new staff coming in and out, and they have been contracting that. So you can, if you don't have trained staff, you can actually have, there are several companies out there, including us, that we can provide those services to you guys.
Oh, we're out of range.
Well, we use all our time. But if there is any other questions, then we are the last one. I don't think that there is nothing else after this one. So.
We do have industry meetings and the business meeting. Really do appreciate you all willing to do this for us.
Well, you're welcome.
Prepare for this. It was something that several of us were interested in hearing about and appreciated, and also appreciate pointing us to that MMA course. Is that right?
Well, AMP.
AMP.
AMP is the Association for Materials Protection and Performance, and it's the combination of the Society for Protective Coatings and the National Association of Corrosion Engineers. And I can get you any contacts or whatever.
Well, thank you.
The preceding was produced by the National Center for Pavement Preservation. More information can be found on the web at pavementpreservation.org. Additional support provided by Michigan State University.